Anyone have heard of universal gates?
NAND and NOR.
NAND and NOR. Why they are called so?
We can get other gates using that NAND and NOR.
Okay, so the other gate operations can be realized using NAND and NOR. So please make a note that NAND and NOR are called as universal gates. Okay, so we'll see how that is possible. And in our syllabus, we have Boolean function realization using NAND and NOR implementation. So today the topic for discussion is NAND and NOR implementation. Implementing Boolean functions using NAND and NOR gates. So what is NAND actually? Not AND. So NAND is what? Not AND. So is the screen visible to you all?
No, ma'am.
No,
No,
ma'am.
no,
No,
no.
ma'am.
Okay, 1 second. Now is it visible? Hello?
Yes, ma'am.
No.
Yes, ma'am.
This textbook contents is visible? No.
Yes, ma'am.
Okay. Okay. So the gate with the bubble symbol in an and gate, if you put a bubble symbol in the output end, what we get is a NAND function, which is not AND. That means I'm passing three inputs X, Y, Z to a NAND gate. So the output given by this gate is AND of X, Y, Z and a complement of the entire expression. Okay. So by applying De Morgan's law, what is the final expression of this? X dot Y dot Z the whole dash. When you apply De Morgan's law on this, what will happen? So this is expanded as X dash plus Y dash plus Z dash, right? So that means what? So every literal is complemented and supplied to an OR gate. So that means a NAND operation can also be realized using invert OR. So is that understood? An invert OR operation is also equivalent to NAND operation. This is what you have to understand here. Following it or not? Hello?
Yes, ma'am.
Yes. Okay. So coming to NOR gate. NOR is OR invert or not OR. Okay. So we will do OR operation and finally not the whole expression. So the bubble with an OR gate with a bubble, we call it as NOR gate. Okay. So when giving X, Y, Z inputs to the NOR gate, what we get is X ORed with Y ORed with Z, the whole dash, a whole complement of X plus Y plus Z. Okay. So this is equivalent to, so when you apply De Morgan's law, this expression turns to X dash dot Y dash dot Z dash. That means what? Complementing each input and then passing to AND gate. So this is called as invert AND. So NOR is always equal to invert and AND. Okay. So NOR is actually OR and inverted. Okay. NAND is actually AND, do AND operation and invert. Take the complement of the whole thing. So it is equivalent to invert and OR. Okay. So is that point clear to you? Hello? So yes. So buffer invert. So we
Excuse
know,
me, ma'am.
yes, yes, ma.
Ma'am, while drawing logic circuits, are we allowed to give three inputs to a gate? Is it
Yes,
correct?
there are. Yes, yes, there are logic gates which will take 3 inputs, 4 inputs, and so on.
Great.
There are
So it's
different.
correct to draw a circuit, I mean, a gate with two or three inputs.
Yes, yes, it's right. It's
Thank you.
correct. There are ICs which will work with more number of inputs. But what we have in our lab is just two input AND gate or two input gates. But gates with multiple inputs are always there. It's always correct using multiple inputs to a gate symbol. So that's true with the OR gate, right? When you are implementing logic circuit with a Boolean expression, all the product terms you will connect using one single OR. So that means that OR gate takes multiple inputs, right? Okay. So invert operation is X. This is a NOT gate. So X dash. So this inversion operation can be realized using NAND as well as NOR. Okay. So if I give a single input to this, and this is nothing but X dot X the whole dash, which is X dash, right? X dot X is always X, and what we'll get as output is X dash. So when X is given a single input to a NAND gate, what we get is complement of X. So it works like a NOT gate as well. So coming to this, X given a single input to the NOR gate, it is X plus X the whole dash. So X plus X is always X, so it gives X dash. So NOT operation is realized using NAND as well as NOR. Is that clear? So how will you realize AND operation using NAND gate? Can anyone tell me? What is AND operation then? Given you're given only with NAND gates, so how do you construct an AND operation? Hello, I've asked a question, please. How will you? So what is AND? A complement of this, right? X, Y, Z whole complement, the whole complement, right? So by connecting two NAND gates in series, for the first NAND gate, if you give X, Y, Z, and to this result, I'm connecting another NAND gate, what is that you will get?
XYZ.
X, Y, Z. Is that AND of X, Y, Z? Yes. It's AND of
Yes,
X,
ma'am.
Y, Z,
Yes,
right?
ma'am. Yes, ma'am.
Yes.
Okay. So this is how NAND is used to realize AND operation, right? Similarly, how is it used for realizing OR operation? You work out
Using two northern. Using two
using
northern.
using
Two
where
northern.
will you put the
Uh,
see
you can
actually you
consider
have to think over each literal has to be complemented using three NAND gates and then supplied to a NAND gate. What will happen? The inputs that are actually fed will be X dash Y dash Z to another AND gate. So while applying complement on that, what you will get? X plus Y plus Z. Getting it or not? Not getting it? So I'll complement each input and then give to a NAND gate. Then what will happen? So what we are trying to produce is X dash dot Y dash dot Z dash the whole dash. Now the final result will be X plus Y plus Z. Yes or no?